Look down at the ground you're standing on. The rock, the soil, even the air you're breathing. It's all so fundamentally, well, radically different from the world that first saw life maybe 4 billion years ago.
Yeah, absolutely. We often think about evolution in terms of biology, genes and selection.
Right.
But today, we're going deeper, literally,
Yeah.
down to the Earth's core.
To see how the planet's structure, its moving continents, and even its air dictated how life could evolve.
Exactly. Our goal here is to unpack the key geological stuff. We need to see Earth not just as a stage, but as a dynamic stage setter.
I like that, stage setter.
These huge, slow changes atmosphere, plate tectonics, they're the real drivers behind the big evolutionary shifts we see.
Okay, let's unpack this then, starting with something basic. The air. When life first popped up, the air was nothing like today. The early atmosphere, say 4.2 to 3.8 billion years ago, it was mostly water vapor and CO2.
That's the picture, yeah.
Yeah.
Thick with water vapor, lots of carbon dioxide.
And almost immediately, life started, well, messing with it.
Kind of. You had these early single-celled microbes, methanogens, showing up maybe 3.7 billion years ago. And what do? They make methane.
Okay, and methane is a potent greenhouse gas, much more so than CO2, especially back then without oxygen, to break it down quickly.
Precisely. So you get this really interesting feedback loop. These tiny microbes are basically pumping up this gas that acts like a blanket.
Keeping the early Earth warm.
Potentially, yeah.
Yeah.
The sun was weaker then, so this methane might have been crucial for keeping water liquid and, well, keeping the planet habitable.
Wow. A biological climate control from the very beginning.
In a way, yes.
Yeah.
But that warm CO2 and methane-rich atmosphere wasn't permanent. The really big shift, the major planetary game changer, came later.
Oxygen.
Oxygen. Series buildup didn't really kick off until about 2.3 billion years ago.
And the culprits were?
Aquatic cyanobacteria. We've got fossils going back over 3.5 billion years. These guys figured out photosynthesis.
Using sunlight, CO2, water.
And releasing oxygen as waste, just dumping it out first into the oceans, then into the air.
And the consequence? Well, it depends on your perspective, I guess. Good for us, eventually.
Right. But for the existing life.
Devastating. Most life back then was anaerobic. Oxygen was toxic.
It was basically a global pollution event. Wiped out huge swaths of Earth's inhabitants, a mass extinction driven by biology itself.
A complete reset. Incredible.
It is life profoundly shaping the planet's chemistry. Now, okay, from the air, let's shift to the solid Earth. How do we even know what's deep inside?
Right, because we can't exactly drill down to the core.
Not even close.
It comes down to listening, doesn't it? Listening to earthquakes.
Primarily, yes. Seismic waves. Seismographs track how these waves travel, their speed, their path. Do they bounce off something? Do they slow down?
And that tells us if they're going through solid rock or something liquid or something dense.
Exactly. It paints a picture of the inside.
Okay.
And it's layered.
Okay, break it down for us.
You've got the inner core. Super hot, but solid, mostly iron and nickel. We even know it's a bit lopsided, asymmetrical, and it's actually growing very, very slowly.
Wow, still changing.
Then the outer core that's molten, liquid iron, sulfur, silicon maybe, creates the magnetic field.
Got it. And then
the mantle, huge, makes up like 4/5 of the Earth's volume. It's rock, but it's hot enough to convex slowly, like really thick soup over geological time. Repeatedly melted and recrystallized.
And finally, the thin skin on the outside.
The crust, which is separated from the mantle by a boundary called the Moho discontinuity.
But for things like continental drift, we talk about the lithosphere, right?
Yes, that's key. The lithosphere isn't just the crust. It's the crust plus the very top rigid part of the mantle. That's the solid shell that's broken into plates.
The plates that move.
The plates that move.
Yeah.
And those plates are made of rock. Now, for anyone studying evolution, you need to know about the 3 basic rock types.
Okay. Igneous.
That's cooled magma or lava. Think granite formed deep down, cooling slowly, or basalt erupting and cooling fast on the surface. Fire formed.
Sediment.
That's the crucial one for us. Formed from layers, bits of webbed rock, volcanic ash. Crucially, the shells and skeletons of organisms all compressed and hardened over time. Sandstone, shale, limestone.
Man, metamorphic.
That's when you take igneous or sedimentary rock and cook it or squeeze it. Heat and pressure change it. Limestone becomes marble, shale becomes slate.
Okay, so 3 types. But here's where it gets really interesting for evolution.
You're one.
Fossils. The actual hard evidence of past life. You pretty much only find them reliably in sedimentary rocks.
That's the critical link. Igneous rocks are too hot, they destroy fossils. Metamorphic rocks might preserve something, but it's usually distorted, baked, squeezed.
So sedimentary layers are like the pages in Earth's history book holding the fossil record.
Exactly. And that leads us to reading that book, Geological Time.
How do we know which page came first?
Well, the fundamental idea came from Nicholas Steno back in the 17th century, the law of superposition.
Simple but profound.
Yeah, in a stack of undisturbed sedimentary rocks, the oldest layer is at the bottom, the youngest is at the top. It seems obvious now, but it was a huge step.
But, okay, how do you compare a layer in, say, England with one in North America? They might look totally different.
That was the puzzle. And the solution came from William Smith, an English surveyor. He realized it wasn't just the rock type, it was the fossils inside.
Ah, index fossils.
Precisely. He saw that specific layers contain specific, unique sets of fossils. Find those same fossils somewhere else, even if the rock looks different, and you know you're looking at the same slice of time.
So fossils became the ultimate correlation tool, linking rocks across continents.
Yeah. Suddenly you could map out geological systems globally. And using these fossils, geologists started chunking geological time into major divisions.
Like eons and eras.
Right. The big one covering most of complex life is the Phanerozoic Eon, meaning visible life. That's the last roughly 545 million years.
Since things started having hard shells and skeletons that fossilize well.
Exactly. Before that, you have the vast Precambrian billions of years of mostly microscopic life.
And within the Phanerozoic.
3 major eras, first defined by John Phillips based on major shifts in the fossil record, the Paleozoic, or Old Life.
Age of fishes, mostly marine invertebrates too.
Then the Mesozoic, Middle Life.
Age of reptiles. Dinosaurs.
Yep. And finally, the Cenozoic, New Life.
Our time, age of mammals.
That's the framework. And we have markers. Oldest sedimentary rocks known are about 3.9 billion years old from Greenland.
Wow.
And that Phanerozoic boundary, 545 million years ago, the start of the Cambrian period, that's when we see the first widespread fossils of hard-bodied things like trilobites and brachiopods.
Okay, so we have the timeline, the rocks, the fossils. But how did, say, fossils of the same reptile end up in both South America and Africa?
Now we get to the really dynamic part, continental drift.
Alfred Wegener's big idea.
Right. Back in the early 20th century, he proposed that the continents weren't fixed, that they had moved, and that once they were all joined together in a supercontinent.
Pangaea. Entire Earth.
He had some compelling evidence. Even then, the fit of the coastlines, especially South America and Africa, it's uncanny.
Like puzzle pieces.
And similar ancient rock layers, and even evidence of ancient glaciers lined up across continents that are now oceans apart.
And the fossils, too.
Yeah, finding identical specific fossils like the Glossopteris plant or the small reptile Mesosaurus on widely separated lands like South America, Africa, India, Antarctica, Australia. It strongly suggested they were once connected. Gondwana, that southern part of Pangaea.
But the big question was how? What force could move entire continents?
That was Wegener's weakness. He didn't have a convincing mechanism. The proof took decades and came from basically 2 main lines of evidence after World War II.
Okay, what were they?
First, paleomagnetism, studying the ancient magnetic field locked in rocks.
How does that work?
Well, when igneous rocks cool, iron-bearing minerals inside align themselves with Earth's magnetic field at that time, like tiny compass needles.
Locking in the direction of magnetic north.
Exactly. And scientists found that ancient rocks from different continents pointed to different magnetic north poles for the same time period. That doesn't make sense unless the continents themselves had moved relative to the pole.
Okay, that's clever. And the second line of evidence?
Ocean floor spreading. Mapping the ocean floor revealed something amazing. It's geologically very young, mostly less than 200 million years old. And there are huge underwater mountain ranges, the mid-ocean ridges.
Where new crust is being formed.
Precisely. These ridges are like volcanic seams where molten rock wells up from the mantle, cools, and forms new ocean floor made of basalt.
Like a conveyor belt pushing the older floor away.
Exactly like a conveyor belt.
Yeah.
And the magnetic evidence clinched it. As the new floor forms and cools, it records Earth's magnetic field, which flips polarity occasionally.
Ah, so you get strikes.
Symmetrical magnetic stripes of normal and reverse polarity running parallel to the ridges on either side. Perfect proof the floor is spreading, pushing the continents apart at rates of, a few centimeters per year. Measurable rates.
That's the mechanism Wegener was missing.
It is. And it led to the theory of plate tectonics. The lithosphere is broken into maybe 8 major plates, and they interact at their boundaries.
Right, so what kinds of interactions?
3 basic types. Separation that's divergent boundaries, like the mid-ocean ridges where new crust forms.
From spreading apart.
Sliding that's transformed faults where plates grind past each other horizontally. The San Andreas Fault is the classic example, moving about 6 centimeters a year.
Causes earthquakes.
Big ones. And finally, convergence, where plates move towards each other.
Collisions.
Right. And this is where things get dramatic, especially when dense oceanic crust collides with lighter continental crust. The oceanic plate usually dives, or subducts, underneath the continent,
Scraping, melting.
creating volcanic arcs and pushing up huge mountain ranges. Darwin actually had an inkling of this process way back in 1838 from his observations in South America.
Amazing. So this constant churning, separating, colliding, it must have huge consequences for life.
Absolutely profound. It's the ultimate driver of large-scale evolutionary patterns. Separating continents isolates populations.
Leading to speciation, unique evolutionary paths.
Exactly. Joining continents brings previously separated groups into contact.
So leading to competition, maybe extinctions, maybe new adaptations.
It sets the whole ecological stage. The history of mammals is a fantastic example of this.
Okay, how so? We classify mammals into 3 groups.
Broadly, yes. Monotremes in the egg layers, like the platypus. Marsupials, the pouched mammals, kangaroos, koalas. And placentals like us, with a complex placenta.
So how did plate tectonics influence their story?
Well, early monotremes and marsupials seem to have been present in southern Pangaea or Gondwana, when Australia rifted off and became isolated very early on.
It became marsupial land.
Pretty much. Its isolation allowed marsupials to diversify incredibly, filling all sorts of ecological niches without much competition from placentals, except for bats and rodents that arrived later, probably flying or rafting.
In South America.
It also became an island continent for a long time, separating from Africa and later from North America by the mid-tertiary.
So it developed its own unique fauna, too.
Yes, a really distinct mix of native marsupials and some early placental groups evolved in isolation for tens of millions of years. Really specialized creatures.
But then Panama happened.
Then Panama happened. The Isthmus of Panama rose and connected North and South America maybe 4 or 5 million years ago during the Pliocene,
Creating a land bridge.
and triggering what's called the Great American Biotic Interchange. Placentals from North America, cats, dogs, horses, elephants poured south.
And the result for the unique South American natives.
Largely extinction. Many of the highly specialized South American families just couldn't compete with the invaders from the north, a dramatic example of continents connecting and reshaping life.
It really drives home how intertwined geology and biology are. A few centimeters of drift per year over millions of years leads to continental collisions that rewrite the evolutionary story.
That's the core message, really. You can't understand the history of life without understanding the history of the Earth itself. The atmosphere, the rocks, the moving continents, they aren't just background. They are the story in many ways. They dictate the possibilities.
It makes you think. The Earth isn't static now. The inner core is still growing. Mountains are still rising. The seafloor is still spreading. We can measure it.
It's happening right now, under our feet.
So given all that ongoing activity, what geological change happening today might be quietly setting the stage for the next major evolutionary shift, millions of years down the road? Something for all of us to think about.
A fascinating question. Well, thanks for joining us on this deep dive into how our planet shaped the life it carries.